Yes. Okay, so welcome to the Thursday seminar of the AFT. It's a pleasure to have today Daniel Robaina from the Max Planck Institute for Quantum Optics in Munich. And Danny will discuss studying 2D lattice gauge theories with Tensor Networks. So please, Danny.
Thanks, Gregorio, very much. So yeah, I'm trying to tell you a little bit about what I did during my time here at MPIQO. So I was asked to give a broad introduction about things and try to spend some considerable amount of time motivating the issue and yeah, trying to explain why we are doing what we are doing. And so for those experts in the audience, if you hear something that you already know, I apologize already in advance, but let's see how this goes. So the outline of my talk will be, like I said, to explain you why we want to use tensor networks for lattice gauge theories. And for that purpose, I will use the sign problem motivation to that. And very in a hand wavy style, I will try to explain you what this sign problem is all about. And when I have done that, I'm gonna explain what are tensor networks in the first place. For those which are not familiar with tensor networks, an IFT is a very high energy type of place, so to say. So this tensor networks business is more in the condensed matter area of physics. So you guys might not know what these are. So then I will go over and tell you what has been done has been done so far with tensor networks, and I will explain the Stringer model in 1D. And then I will go over and try to explain what happens when we go to 2D, and then I will explain the work that we actually did. Okay. So as you probably know, lattice QCD is a way of studying QCD on the lattice, which allows for a non-perturbative definition of it. And it has had tremendous success in calculating a lot of aspects of QCD, like the mass spectrum and other quantities like the actual charge of the proton, which enters beta decays. And there is a whole industry of groups and a lot of activities around studying lattice QCD. And so over the last 40 years, it has been very successful in describing and in predicting a lot of interesting aspects of QCD, which otherwise we would not know. But still there are like some unknowns that lattice QCD are some problems with the formulation, which is basically that the lattice QCD simulations are not able to, or generally speaking, are not able to access finite density aspects of the theory under study. And so, for example, whether there is a critical point in the QCD phase diagram, or whether there are other phases of matter, these are all open questions that with the current techniques that we have for lattice QCD, we cannot address. And so people have come up with workarounds, and people have tried imaginary Kemal potential, they have tried Taylor expansions, they have tried reweighting, they've tried Lefschetz thimbles, Langevin methods, and a lot of things. But ultimately, they are faced with the so-called sign problem. And so the idea in the next few slides is to explain you why this happens and why this appears and why is it a problem. So when you have, for example, the free scalar field theory, when the usual path for studying this theory in the Monte Carlo approach is to make an Euclidean rotation, a weak rotation to Euclidean time, and then the action becomes positive definite. And what you can do is then use this weight as a probability distribution, as a Boltzmann weight, and generate a set of configurations which are distributed according to this weight, and then you can sample that. and you can calculate expectation values just by taking normal averages. But what happens at finite density, if you just put some finite chemical potential into the Lagrangian density, when you do the same program and you try to do a weak rotation, what you find is that actually you get a complex phase multiplying the Euclidean action. And so a priori, this is a problem. And I will try to explain you why this is a problem. So, the thing is that we have an oscillatory weight function that one needs to sample. So when you generate an ensemble, you have a probabilities distribution, and what you do is you generate configurations according to this probability distribution, and then you just take expectation values in this way, where the configs are taken from this already simulated ensemble. And then you can always do, what you can always do is just multiply and divide by some function h, and instead of sampling this initial probability distribution p, to sample a different one, which might be h, and then you can always correct for this. And this technique is called reweighting. And I'm talking about reweighting because I find it very intuitive way of understanding how the sign problem appears by trying to solve it in a reweighting type of approach. And maybe you understand what I mean in the following slides. So the idea is then that you have your probability distribution P, and instead of sampling P, you sample H. And if P and H are close enough to each other, you can use this technique to calculate the expectation value. If H and P are not close to each other, then still this mathematical identity holds, but you will have a harder time having low error, say. So where can reweighting bring us in this problem? So imagine that now we have this oscillatory probability distribution, and for this toy example, I just take, imagine that I have some action which is positive definite, and then a cosine function just to emulate this oscillatory behavior. And so it is clear that we cannot sample this because there is no way that we can design an algorithm that gives us a given config with negative probability, right? I mean, this doesn't make any sense. So we need a positive probability distribution. So we can try and play this game and introduce some auxiliary function h here. And then, like I said, calculate expectation values according to P just by taking this ratio. And so now we are calculating this expectation values in terms of H, but we have to correct with this reweighting factor. And so we have at the end two partition functions, set P and set H, and set P was the original one, which is oscillatory, and now set H is one, which is a helping, say, which has the property that H is bigger or equal than 0. So the question is, how do we choose H in a sensible manner to perform this strategy? So is there an optimal positive function that we can reweight from? And for that, one thing that we can do, I mean, is, if I go back to the last slide, you will see that this factor here, this reweighting factor, this will enter all the expectation values of any observable that we will calculate. So we better have it with pretty good precision, because it will, the error that we commit here, that we have here, will translate to all expectation values that we have. So what we can do is try to choose H to minimize the error on this reweighting factor. And this is exactly what I have calculated here. So, and if you see this, one obvious thing that you could do in order to minimize this relative error on the reweighting function is just to take H to be the absolute value of the phase. but this leaves us with having to calculate the average sign. So now if I plug in H into my reweighting factor, what I have is that I have to calculate very accurately this sign. And this is where the origin, I don't know if it originally was this way, but at least this is like the sign problem, in the sense that this is the sign that you have to sample. And this is hard. And it's hard because of basically two reasons. One reason is that if you write this reweighting function, you see that it's nothing but the ratio of two partition functions, the one with probability P divided by the one with probability H. And the partition function is usually in the exponent, it's related to the free energy of the system. And as the volume gets bigger, the free energy, it's an extensive quantity. So the difference between those will become bigger and bigger. And so you first have the problem that it has a very bad signal. It's very small. It scales very badly with the volume. And on top of that, if I plot, for example, for this toy model that I had, if I plot on the x-axis mu, which is basically the Lagrange multiplier that I introduced, denoting the chemical potential, this is nothing but the frequency of how much is this function oscillating. And so you see that as I increase mu, the function oscillates more and more. The error grows exponentially, the sign decreases exponentially, and the signal versus error gets worse and worse. So maybe at small mu, we can do things, but as soon as we want to do big mu's, big densities, say, the problem gets more severe and more severe. And this is what is called an NP hard problem. And so it's a hard problem, say, and you need a lot of exponentially more statistics to overcome this, which is not feasible. Okay, so this was my introduction to why for finite density, the current techniques of Monte Carlo face this so-called sign problem. And now I'm gonna go and propose some alternatives. So maybe I stop here for a couple of seconds if someone has any questions. If not, then I continue. Okay, so what are the alternatives? So the alternative is, of course, tensor networks. So what are tensor networks in the first place? If they are supposed to solve this problem, we should know what they are. So a tensor, imagine that you have an n-particle one-dimensional quantum system, like for example, a spin chain. So if you would like to describe this quantum state, you would see that you need, you have n degrees of freedom. And so you have a big tensor here with a lot of legs. And how many do you have? Well, you have the product of the dimensions of all the local Hilbert spaces of each of these degrees of freedom. In the case for a simple spin system, for say s equals 1/2, you would have 2 to the n parameters that you need to give in order to fully parameterize the state. So this is of course a lot of parameters. So for for n equals 10, the things start to become complicated for storing them, for example, in computer devices. And for n equals 4, 14, and 15, the things are becoming to be unfeasible. And so the idea that Steve White had in 92 was to say, well, maybe we don't need so many parameters. Maybe we can get away with a different parameterization of this quantum state. And so what he introduced was the matrix product state, which is nothing but a state which is described by a set of tensors where you put one tensor on each side. And this tensor has one physical index, which is the same index as here. So it denotes in which state this degree of freedom is. And then it has additionally some virtual legs that allow for communication between the neighboring sites. And this, if you do it this way, then what you have is just one matrix. Say in 1D you would have one matrix, because this is you have two legs, two virtual indices, and for each of those you will have the dimension of the local Hilbert space. For example, for S equal 1/2, you would have two tensors per site. One which describes the state up and one which describes the state down. And these are matrices. And so you multiply them all together in order to create this matrix product state. And so what you have done effectively is that you have gone from an exponential scaling with the number of sites to a polynomial scaling, where you just now have on each side, you have chi-squared, it's the dimension of the virtual indices. And so you have two of them times n, because you have n sites, and then times the dimension of the local Hilbert space of each of these sites. So what you have done is to have gone from an exponential scaling to a polynomial scaling. And this is already quite interesting. But of course, the straightforward question would be, well, yeah, but this ansatz is of course much more restrictive than the general ansatz. So we have to lose something. Nothing comes for free. But actually, we don't lose so much. It depends what are the questions that you are asking. And so this brings me to my next slide, which introduces this notion of entanglement and the area law of entanglement, which has a priori nothing to do with the area law of confinement that we are used to from QCD or from other confining theories. This is a different area law. So if you have a pure state, you are able to define what is called the density matrix. And what you can do is to also define yourself a reduced density matrix, which is basically you split up the system into an A part and a B part, into two subsystems. And if you want to have the reduced density matrix of A, what you do is you trace over the degree of freedom which belong to B. And this is what is written here. And there is another quantity that you can calculate once you have this reduced density matrix, which is the entanglement entropy. This is just how much are those two subsystems entangled. And this is defined in this way. It's like the usual von Neumann, I think it's called entropy type of calculation, say. And a priori, you would think that for most quantum states, the entropy is an extensive quantity. So the subsystem between the entropy density, the entanglement entropy between subsystem A and B should grow like the volume of the subsystems that you have traced over. But actually, the interesting aspect of it is that for specific states, namely for ground states of physical local Hamiltonian, which have also a gapped physical local Hamiltonian, it was proven that actually this only scales like the boundary of the two subsystems. So not the whole, not the area of A is the quantity that you have to look at, but the boundary. And this is what is called the area law of entanglement. And the interesting thing is that these type of states that satisfy this area law are a very tiny corner of the whole Hilbert space that you could actually define. And the interesting states, the ones that you mostly would like to know and get to know more closer, let's say, are the ones that actually satisfy this area law. And this is true, for example, for ground states, like I said, of physical local Hamiltonians. And it's a very tiny corner. And in fact, what happens is that you can engineer certain tensor network parameterizations, like the one I introduced before, like matrix product state, which automatically obey this law. So they seem to be actually targeting already this tiny corner of the full Hilbert space, so that you are already in the neighborhood of this Hilbert space where you would like to find interesting states, like the ground state and maybe a couple of excited states and so on. And this is what makes tensor networks so powerful, say, is that they already target this corner in the full Hilbert space. And actually the rest of the Hilbert space is mainly very hard to access. Even you would have to, if you would do a calculation like estimating how long would it take you to reach every state in the Hilbert space, you would see that if you start with a very low entangled state, it would take you an exponential amount of time to really visit every state in the full Hilbert space. So most of these states that are here, they are actually not relevant and not even accessible from a experimental point of view, if you want. Okay, so let me recap what we learned about tensor networks so far. So tensor networks are just a quantum state ansatz that you say, well, I'm going to parameterize my state in this way. And the interesting aspect is that the number of parameters that you have to tune grows polynomially instead of exponentially, like we learned. And they target the area loss sector of the Hilbert space, which is the sector in which most ground states actually live, of interesting Hamiltonians. And we learned that each degree of freedom is represented by a tensor, which has one physical leg of dimension little di, and one or more virtual legs of dimensions chi or capital D. People like to use chi or d in order to denote the dimension of these virtual indices. And whenever we see an edge between two tensors, this means that there is a sum going on between those. This is just a pictorial way of representing the state. It's just you put the tensors, and when you connect them, means that it's summed over this index. Okay. And then, of course, if you open this toolbox of tensor networks, say, you find out that there's a lot of research done already, and there's a lot of clever people that engineered very interesting algorithms in order to tune the parameters, to update the parameters, which you need to calculate in order to represent the different states that you are interested in. And so you see that the people have been using these techniques for years, and a lot of interesting things. I learned a lot of things by studying the different algorithms and ideas people had related to tensor networks. Okay, so of course, now let's go back a little bit to our original goal, which was to use those tensor networks to simulate lattice gauge theories. So there are of course pros and cons of following this approach. And let me start with the pros. So since we work in the Hamiltonian picture, or more naturally tensor networks, although you can also use tensor networks to parameterize path integrals and things like that. So it's not that tensor networks only work with Hamiltonians, but for the sake of this talk and for what I'm going to tell you, let's assume that tensor networks work in combination with the Hamiltonian picture of quantum mechanics. And so since we work in the Hamiltonian picture, no sign problem, because there is no Monte Carlo approach that we have to do. And in principle, you have real-time evolution, and you have finite density, and all these nice things. And since you work in the Hamiltonian picture, you don't need to include time as an additional dimension. So this saves you a little bit of computer time as well. And so also a consequence of that is that you have the typical outcome of a tensor network's calculation is you end up with a state. So you had an ansatz, which was this tensor networks, and you end up with a state, which means that you have tuned all the parameters of your tensor network in a clever way. So what you have is a state, and then you are able to investigate this state further. You are able to calculate reduced density matrix. You are able to find out more what the entanglement structure of these states is. And this is something very interesting because usually in the more traditional approach of Monte Carlo, you have a gauge ensemble, and you are never interested in individual states, or very, very rarely you analyze a very particular state. You are interested in the gauge average of some expectation values. And so also some formulations, like the ones I will introduce you in this talk, they aim at the thermodynamic limit already. And this is also very interesting because you don't need any subsequent extrapolation to the thermodynamic limit. But of course, there are also some cons, and the contraction of these tensor networks can become very expensive. So summing over all these edges can become very expensive with increasing spatial and bond dimensions. For example, for MPS, it's the case that the runtime complexity of contracting an MPS grows with d to the 3, so where d is the bond dimension of your MPS. And for example, for d equals 2, it goes like, so for space dimension 2, it goes like d to the 10. So it can get pretty expensive very rapidly, but still it's a polynomial scaling, although the exponent might be very large. And then Hilbert spaces of gauge theories, which are based on Lie groups, they have to be truncated in a consistent manner. You cannot keep track of an infinite number of tensors for a given site. You will have to restrict yourself to a given representation or something. And this can be done, and it has been done in the past. So there are studies where with MPS you investigate some SU2 gauge theories, and people came up with ways of systematically truncating the local Hilbert spaces of the individual degrees of freedom. And also the question of the continuum limit is a very interesting one, and there is no general recipe to take continuum limits of tensor networks calculation. And there are a lot of people working on that and trying to figure out ways, but the field is not so mature as the Lattice QCD field, say, where there is almost always a well-defined recipe of how to take the continuum limit of a given quantity that you are calculating. And so far, since the field is a little bit is young, there are no dedicated tensor network codes that implement particular aspects of gauge theories. So you basically have to write your own code, and this can take some time and can be painful in general. Okay. So,
Danny, one question. How should one understand the continuum limit in this context? Does it involve the limit in the bond dimension also, or only spatial?
So, so far, so I know of one study which they did continuum limit calculations, and so what they do is they do it at finite bond dimensions. So it's there are people that argue that in order to get a true continuum limit or a true representation of the continuum limit, what you need is actually infinite bond dimension. But at the practical level, what people do is first they make sure that their results are converged in bond dimension, and then they take the continuum limit by taking, for example, one of the couplings of the Hamiltonian. They know that it's related to the lattice spacing, and so they make some extrapolation in this parameter. I don't know if I answered your question.
Yeah, okay, thanks.
Yeah, so basically by tuning the parameters in the Hamiltonian.
Just at this point, I also I mean, in principle, you can compute, well, I don't know exactly how, but you should be able to compute correlation functions,
Yeah.
at least spatial correlation functions, or even time correlation functions as well. So I think that's the way to determine the continuum limit, because actually the number of A's that you put is just the discretization of space, right? So you would like to have the correlation to grow as you tune the parameters, and more points to get the same correlation function, right? So somehow it looks like a well-defined problem to see what the critical point is, okay? Isn't it?
Yeah. So sure. I mean, personally, I haven't thought about this too much, but there are people that are thinking about this a lot, and in the past, there are people that claim to have taken the continuum limit in a consistent way. I'm not saying that it's not possible. I'm just saying that from what I was able to learn, it seemed like something that was not fully established, say. And, okay. So now I would like to talk a little bit about the one gauge theory that you can study with tensor networks, and people actually did, which is the Schwinger model. And well, basically this is a QED in 1+1 dimensions. And
sorry, this just a little thing that I didn't ask you at the beginning. When you say 2 dimensions, you mean 2+1?
Yes.
Because it's not the standard way. So, because time is there. So it's 2+1. So this is 1+1.
It's 1+1.
And then
MPS.
you will go to 2+1, right?
Yes.
Okay.
Yeah. So at the end of the talk, I'm gonna talk about 2+1. Yes. And now I'm just introducing like MPS, which is for 1+1. Yeah. So the Schwinger model with MPS is something that people have studied, and well, you start with QED in 1+1 dimensions, and it's actually a very interesting model to study because in 1+1 dimensions, this model exhibits confinement between fermion charges in a very trivial way, but still it exhibits confinement. You can understand that in a very hand-wavy way because the potential between two static charges goes like 2 minus d, where d is the space dimension, and if you have t equals 3, you have 1/r, which is the usual Coulomb potential, and if you have t equals 1, you have a linear potential. And this is by no means any rigorous claim or anything, but it's a fact that it exhibits confinement. So if you want to study this model on the lattice, you have basically a couple of things to do. So one way of doing things is like the Wilson approach, the one that we all know about, which is to take the Lagrangian and discretize an Euclidean of d+1 lattice. Now d is the space dimension. And so you end up with a Lagrangian density. For those who know a little bit of lattice field theory will recognize this is a Plackett operator, this is the Wilson action, and you will have to choose the discretization of fermions, which is favorite to you, and put it in there as well. But this is not the only way of discretizing the theory. So 1 year after Wilson made his seminal contribution, Kogut and Susskind, they explained how to do this in the Hamiltonian approach. And there they had a d-dimensional lattice, and they basically came up with a Hamiltonian, which was describing the same kind of theories. And it's a little bit different. The formulation is a little bit different, but you can trust me when I say that it's the same theory, and it's just a different way of parametrizing it or to expressing the theory, say. So what you have is basically the gauge degrees of freedom are split into 2 parts. Like you have a phase here between the 2 fermion fields, and you have a pure gauge part here, and these 2 quantities are conjugated to each other. So like x and p, they have commutation relations equal to I. The same way L and theta obey the same commutation relations. So the usual canonical, not the usual, but some derived version of the canonical quantization program, and you end up with this Hamiltonian. And they assume the staggered formulation, which is a formulation in which you split the fermion fields into even and odd sides. That's why they had here this -1 to the n, because the even sides have the matter and the odd sides have the antimatter. And in the continuum limit, these two fermion fields will merge into one Dirac spin or so. So if we want to use tensor networks, we should use this type of approach. And people did that. And so like 3 years ago, Mari Carmen Banuls, which I also work with here at MPIQO, and her collaborators, they made this approach to work, and they actually calculated, they simulated the Schwinger model in 1+1 dimensions with an MPS ansatz. And they did so even, I don't want to go into a lot of details. If there are questions, I can answer them. But basically, what they did was to put two flavors and create an imbalance of flavors by adding a chemical potential. And so this would be a situation in which standard Monte Carlo approach would suffer from the sign problem. But in their approach, of course, there is no sign problem. So they were able to map out the complete phase diagram, also take the continuum limit, and basically solve the Schwinger model completely. And so they did so at finite density, and they found phase transitions. They map out the complete phase diagram. They were able to calculate two observables like the fermion condensate and so on. So basically, they solved the full Schwinger model at finite density.
Sorry, can I ask you, it's not an analytic result, right?
No. This is all numerical.
Okay.
Yeah. This is all numerical. So they start with an MPS ansatz, and they run their DMRG, was it in this case? It's a procedure to optimize the tensors in the MPS in order to lower the energy and lower until you converge to the ground state. And once you have the ground state, you can work with that. So it's a numerical approach, yeah. So given the success of the Schwinger model numerically, the question was, well, how can we go to more dimensions? What can we do in 2 dimensions, in 2 space dimensions? So beyond 1D, the first thing that we have to think about, let me check the time.
Well, it would also be very interesting to look at things like QCD in 1+1, where you have the meson spectra, derived by Toft long time ago.
Yeah.
And there I mean, it's just not U1, but it's a 1+1 theory, which is confining, of course, obviously, as you said, but that has a lot of information that can be obtained more or less analytically, because in the Toft did it, and you could still, I mean, I don't know how difficult it is to implement it numerically in this case, but it's an interesting goal that you could be able to do in this way.
Yeah.
I don't know if anybody has tried, but anyway, that's an interesting thing to do.
They did the Schwinger model with a gauge curve of SU2. They not only U1, but also SU2. This was a follow-up paper that they did. So I guess that it wouldn't be, I don't know how complicated it would be to go from SU2 to SU3, but they did it with SU2. Okay, I don't know how much time I have. I don't know. I just
20 minutes.
Okay.
Roughly.
Yeah. Okay. So if we want to go to beyond 1 dimension, we first need to start thinking about tensor network ansatzes in more than 1 dimension. So people have done this in the past, and they came up with a way of doing that, which the tensor network that you arrive at is what people called back then. This was a work by Frank and Ignacio, and they called them projected entangled per state. The construction of these states is quite interesting, but I don't want to go into the details. Just say that it's a generalization of the MPS. And basically, if an MPS is a 1-dimensional array of tensor, a PEPS is just a 2-dimensional array of tensors. And now your building block is not a matrix anymore with 2 virtual indices, but you have a tensor which has 4 indices plus the physical index, plus the index that gives you the information about the state in which this degree of freedom is in. And in the same way as MPS, the PEPS, they obey the area law. So they are this area law of entanglement, which makes them good candidates for describing ground states. And they are dense in the same way as MPS are. And what this means is that if the bond dimension is increased, eventually you will be able to parameterize any Hilbert space in the Hilbert space. And PEPS are also in this, share the same property. And contrary to MPS, the PEPS can do more. Namely, they can handle polynomially decaying correlation functions, which MPS cannot. MPS, the correlation functions in MPS, they are always exponentially decaying. And with PEPS, you can actually describe criticality. And the next thing, to make this even more appealing, say, we can try to make them translationally invariant. And the first thing that one could think about is, well, let's put a finite PEPS and impose periodic boundary conditions on all directions. No? And this would be nice. It has translational invariance, but still it would of course suffer from the fact that there is a boundary. It would have finite size effects. And then this other idea came, which is the idea of this infinite PEPS, in which you basically, what you do is you define your tensor networks basically as an infinite tensor network. And this is the approach that we chose, and I will explain more about this iPEPS in the following slides. So the idea is that you have translational invariance, you don't have finite size effects, so you are truly living in the thermodynamic limit. And these iPEPS, they inherit all the nice properties from PEPS that we described, in the sense that they can describe polynomially decaying correlation functions, they are dense, they obey the area law and all that. And one thing which makes them special is, of course, since it's an infinite tensor network, you only need to keep track of a given unit cell. So you define yourself a unit cell, and you only and this unit cell is repeated infinitely many times in all directions. And so, for example, unit cells that you can think of is like maybe just one tensor, which is repeated all the time, or maybe a 2x2 array where you have A, B, B, A, and then you repeat it all the time, or even more complex unit cells like that, also 2x2, where but now you allow for A, B, C, D, or even 2 times 3, A, B, C, D, E, F, and you repeat this everywhere. And this defines you a tensor network ansatz, and that's what an iPEPS basically is. It's a 2-dimensional tensor networks where you have defined a unit cell which is repeated infinitely many times in all directions. Good. So, any questions before I go to the actual meat of the talk? If not, okay. So now the goal was to start with a simple thing, a simple gauge group, which we do not want to truncate. So it's a finite gauge group. It's set 3, and we want to just, as a proof of concept, show that we can parameterize, or we can simulate a lattice gauge theory based on a gauge group with an iPEPS setup. And so for that, I need to first start defining what the theory is. And so the theory is basically defined by a Hamiltonian, which has an electric and a magnetic part. And so you have your 2D lattice, and you have your links residing at the edges, which are of dimension 3, because we want to simulate set 3. And you have some E² operators acting on those links, which are just single site operators. And you have placket operators, which is the type of operator that you need in order to have gauge invariance, basically. And these are just the usual placket operators that we know. And so we have 2 operators: E, which is giving us the eigenvalue, the electric field eigenvalue, and then the U's, which are the ones that lower and raise the electric field on the individual links. And E takes values in -1, 0, 1. And then, of course, in order to have...
Can I ask you a question?
Yes, sure.
Why not C2, which would be some kind of Ising model?
Yes.
That's easy.
Yeah, that's also a good question. I think we didn't want to do Z3 because somehow we wanted to have a symmetric spectrum, so to say. We didn't want 0 and 1, but we wanted to have -1, 0, and 1. I cannot remember exactly why we decided so, but you're right, it would be much easier. But for some reason, which I cannot remember right now, we wanted a symmetric spectrum on each of the... But you're right, in principle, we could have done Z2 exactly in the same way I'm presenting this.
Okay.
But we decided that for Z3. Maybe, well, okay, let me continue. Maybe the question becomes clear. So apart from these operators, we need to define a gauge symmetry operation, which is basically to define an operator which makes the Hamiltonian block diagonal. And this is an operator which acts on the vertices and which ensures that when acting on a state, this state has a well-defined charge. And the charge is -1, 0, and 1 again. So not every state that the iPEPS is able to parameterize is guaranteed that will have this property. So we will have to do something special in order to enforce this property. Yeah. And maybe this is related, although I'm not so sure, but maybe this is related to what you were asking. Maybe with n odd, you have this, and if not, you don't, but I'm not so sure. You may know better. So the thing is that if you have n going to infinity, you recover U1. But I am not so sure if you have this with if you include even n's. But I'm not sure. Maybe there is a way as well. But if you consider only odd n's, for sure this is true. Okay. So what's hard about this approach? Basically, the hard part is these 4 body operators. The plaquette operator and the Gauss law operator are the ones that we need to care about. These are the hard parts. So the ground state of energy in some limits would be such that when we put G square, when we send G square to infinity, this is the term that will dominate and will bring all the links into the 0 state, and we will have 0 energy. In the other regime where G square is close to 0, this is the guy that will dominate, and we will have an energy of minus the number of plaquettes. Just to have an idea of in which range the energy should move. So now we have to find the ground state, and the strategy would be to have an imaginary time evolution, which is very similar to what people do when they do lattice QCD, which is basically apply e to the minus beta h to some random state, and in the limit of beta to infinity, we recover the ground state. And for this, we need to come up with some factorization, they call it, which is nothing but the Baker-Hausdorff-Campbell formula for splitting up this Hamiltonian into its electric and magnetic part. And then if you take the delta tau small enough, you are making smaller errors. And so it will be n steps, every update will be n steps of this sequence. So in this sequence, the hard part is, of course, this one. So the electric part are just single site operators that we know very well how to apply. But the problem are these 4 body operators here. And for this, I'm going to introduce this technique, which is it's very important for the project. And it turned out that it was the critical aspect that we had to find. But it's very technical and a little bit complicated. So let me just briefly tell you what it means. So basically you have a plaquette, which has 4 links. And the idea is we want to implement this operator, e to the minus delta tau h plaque. So what we want to do is we introduce an ancillary degree of freedom, which is a helping degree of freedom in the middle of this placket. And we initialize it in a completely symmetric state. And then what we start doing is we start to apply two-body gates, they are called. I mean, they use this notion of gates because it's more cool, because it's quantum computing gates and it's just quantum gates, but it's nothing but two-body operators. So they apply this, we apply these two-body gates between the links and the ancillas. And in this way, we entangle the ancilla with each of the links of the placket. And we do that with all the four. And then we are able to put this part. So this is the in state, which was the ancillary degree of freedom. And these are the four links in the placket. And so now we did this part. We made this sequence of two-body gate. And now we apply a local operation, which is everything is engineered. So everything is, you have to make it work for your particular case. It's nothing general. You have to think about that. And so now you make a local operation on the ancilla and you undo this sequence of two-body gates again. And what you end up, if you choose this two-body gates clever enough and this local operation clever enough, what you have done is you have moved this to the actual degrees of freedom that you want to apply it to. I know this sounds very anti-intuitive, but it works in practice. And here I have, in the next slide, I have, if people are interested in know exactly how this works, I can show them. But the takeaway message of this starter trick is that it's non-trivial to apply this four-body operator at once. And if it's an exponential form, it's even harder. So this trick allows you to express this four-body operator as a sequence of these two-body operators. And the good thing is that common iPEPS algorithms, they are very good at applying two-body gates, but they are not good at applying four-body gates, four-body operators, say. So by writing this in this way, we were able to implement this four-body operator. And this was a very crucial part of the project. And so here's, if someone is interested in exactly how it works, it works. But we don't have to go over it now. But one thing is that we can use the same trick to enforce Gauss law on the vertices. So you define yourself a projector, which just projects vertex X to charge Q, which is just a usual projector. E1, E2, E3 are just the electric field operators on the links. And by applying this on vertex X, this acts on the four links and projects it to charge Q. And we can do the same thing. And this is also a four-body operator. And we can do by choosing different gates and by choosing different local operation. We can do exactly the same thing and implement this operator, this four-body operator as a sequence of two-body gates and end up with having projected the links degrees of freedom to the charge Q that we want. So this was all very non-trivial to figure out, but at the end it worked. And so with this in mind, we have now to choose our iPEPS unit cell, and the unit cell that we chose was to have a 4x4 unit cell. And here we have 8 links, which are these green circles. We have 4 vertices, which are these blue diamonds, and we have 4 ancillas, which are these yellow squares. And we include these ancillas and these vertices precisely for doing what I just told you, just to implement this four-body operator for the placket and for implementing Gauss law on the vertices. And maybe I am a little bit short in time, so I'm gonna skip this part, which is basically telling you how to calculate expectation values on iPEPS, but it's a bit technical, so I'm gonna skip it. If people want to know how to calculate that, I can go. I want to skip that too. These are consistency checks that we did in one-dimensional stripes of plackets, and so here are our results. So at the end, we wanted the ground state energy And for the case for which there are no static charges, we have these points, which are basically these two curves for one dimension of the iPEPS state equal 4 and 5. And what we also did was to project to vertex 1 and -1 to simulate as if we had static charges 1 and -1 living on these vertices. And then you get a different ground state, which is the one which is here, also for d equals 4 and 5. And it's known that the Z3 theory in 2 dimension has a phase transition, a first order phase transition. And we were able to see that by noting that we had a discontinuity in the derivative. So if we follow this line and we follow this line, we see that they don't match. The slope of these two lines do not match. And we could further investigate that by calculating explicitly the derivative. And we see that we saw a jump basically at some value of g squared, which was clear indication that there was something going on there. And it is known that the Z3 model in 2 dimensions, 2 space dimension, has a first order phase transition. And so we were able to see that, which was very nice. Another thing that we did was in order to enforce our findings, to calculate also Wilson loops, which we can also do. It's a little bit more costly, but you can do that. And for Wilson loops, what we did was to basically calculate them, the expectation values of them, and fit them to straight lines. And so here's the region of small g squared, here's the region of large g squared. And if you plot the slope, basically this is the slope of these lines here, you see that from 1 g squared on, the slope suddenly starts to rise, which is an indication of also something going on there. Yeah. So now maybe I can show you very quickly this thing, which is this electric field maps that I had fun building. So these are our unit cells. So these are the links of our unit cell. This is just a pictorial representation. And so here is g squared. And as I increase g squared, the value of the links start to decrease eventually until they disappear completely because they are 0. And if I do the same thing, but I first project to 1 and -1 in these static vertices, I start increasing g squared, and at some point the phase transition it confines the electric field into what it should be. I don't know, maybe just to play around a little bit. Fine. And then I don't want to talk about the errors, I don't have time. Let me go to the conclusions. So I hope I have convinced you that the starting gauge theories in the Hamiltonian picture is well motivated. There was some tremendous success in 1+1 dimensional theories with MPS. And this, we tried to go to 2 dimensions with this iPEPS ansatz. And we implemented this 4-body placket operator as a sequence of these 2-body gates, which was a crucial aspect. We also used the same trick to implement the Gauss law. We were able to see a lot of physics and a lot of phenomenology of this model. We were able to locate phase transitions and extract some properties of this theory in 2D. And well, it was the first lattice gauge theory calculation with iPEPS so far. So this is also something that we are very proud of. And of course, the open issues are that we didn't include any dynamic fermions so far. So this is something that we have to think in the future. And with this, I want to conclude. Thanks.
Thank you very much, Dani, for this very clear and interesting talk. So, other questions?
Can I ask you one thing? Okay, in principle, does it correspond? I'm trying to figure out how to map this that you're doing to the ordinary, let's say 2+1 Z3 theory on the lattice. and sort of, because it's like taking the continuum limit in time, one of the directions, right?
Yes.
While not in the other ones, of course. So you, so this, there is no discretization. Yeah. So. No, I'm just trying to want, because normally, what I mean, in principle, the order parameter, what would happen in the theory is that at low temperatures, which probably correspond to G square small or so on, then you have a spontaneous breaking of the symmetry, right?
Mm-hmm.
And then once because that's with the phase transition, when you rise this value above some critical value, then you recover sort of that the magnetization is zero or whatever. I mean, the average value. So that's the type of thing. You get these bonds which are sort of trapping the in this region. So I guess that's the picture. Trying to make it compare with the vision that you might have when you do lattice gauge theory. The same theory, but in lattice gauge theory.
Yeah. For me, it was also a very hard shift in paradigm to think about things in the way they think here. So for me, still, I have a lot of questions and things that I don't understand how to translate between the two worlds, and so it's still for me open issues everywhere.
Okay.
May I have a question?
Sure.
Okay, how you compute the entanglement entropy for some region here? I mean, and see how it behaves at the phase transition, or some feature at the phase transition?
I think there should be a way of doing that. Yeah, we haven't done that, but I don't see why we couldn't. Maybe it's interesting to look at. Yeah, good point.
And so in principle, you can also do time evolution, right?
Yes.
Have you tried to do that, or
no? We haven't. Yeah. So it's a lot of things that you can do. Of course, I mean, once you have this iPEPS code working, you can start doing a lot of things. Yes, but for now, this is what we concentrated on. But yes, of course, I mean, there are people that do real-time evolution of iPEP states, and it's interesting.
Can I ask you another question?
Yeah.
Just maybe a little bit related to that, to the fact, because the calculation that you have done numerically, but with normal computers, right?
Yes.
Ordinary computers.
Yes.
But is there some way? Because I think the one-dimensional, 1 + 1 dimensional problems have been sort of try to cook up a machine that will directly do the simulation. I wonder if there's something similar concerning these two-dimensional arrays, some kind of device, electronic device that implements the tensor network.
Yeah, so it's actually a very good point. I mean, the people in my group and Ignacio, they are thinking about these things. They are thinking about this notion of having simulating Hamiltonians which simulate other systems. No? So you have a system which is a quantum system that simulates another quantum system. So there are people that are looking for this. Yes, I have no clue how this works. I have not studied this or worked on that, but yes, this is ideas that people have, and this notion of mapping the Hamiltonian that you want to simulate this quantum system onto another quantum system, which you can handle very well, and using this second quantum system to simulate the first one. So yes, this is something that people are thinking about, but I cannot give you many more details. I'm afraid. Maybe Germán, you know more about that.
Well, I mean, especially what you said, right? I mean, there, I don't know, kind of Hubbard model, for instance, this can be already implemented, right? But these are simulations. This is more like simulating these Hamiltonians using some ion traps or Paul atoms, things like that, right? So this is the same story, right? But this, I think this is in principle independent of the tensor network. It's a matter of realizing the Hamiltonian, not really the tensor network, I think, right? You just have a physical system whose effective Hamiltonian is the lattice Hamiltonian that you wrote, right? This is what you would like to do. I mean, and when you have done, it's a different thing, right? It's implementing the tensor network to find the low energy.
And an analogical computer, yeah, something like that, yeah. Okay,
yeah.
Yeah. I see, yeah. It's not the same. No?
Not the same.
Further questions? So I have a question. You mentioned that iPEPS allows you to have effectively infinite time and infinite space dimensions. So in practice, when you implement it, is there a parameter controlling that? I mean,
so they still have a finite bond dimension. So this is an iPEPS is defined by a unit cell, which is just repeated infinitely many times. And this infinite.
Yes, but in practice, this is not infinite. So how do you do it?
Yeah. Okay. So then I will have to talk to you about this. So what you do is you define a unit cell, and when you want to calculate expectation values, what you do is you hope to have an effective description of the environment around this unit cell. And this is where all the information about this infinite tensor networks gets effectively coded. In this, imagine that you want to calculate a two-body operator, which you want to put here, but you need to take into account the infinite tensor network which surrounds these 2 points. So you define what is called the environment, and you have to come up with an effective description of what everything which is around these 2 points, and you encode this in these tensors, which are supposed to give you an effective description of all the environment around these 2 points, and this has to be converged. So this is
isn't it like mean field in some sense? Some kind of mean field?
Yeah, probably you can think about something like that. I don't know exactly about mean field, whether this applies to this case, but probably there are some connections.
Because in mean field, you do something like that. You assume first an environment, and then it has to be self-consistent in the sense that you assume an environment, you compute the thing, and then the result, it corrects the initial value that you put for your bound for your environment, and then it has to be consistent. That gives an equation, which is the one you solve. So maybe it's in this context is something similar to the mean field approach.
Yeah, it could be. It could be. So in this approach, what you do is, so if you want to calculate an expectation value here, what you do is you, for example, if you want to calculate what is the environment contributing to this corner tensor here, so you take all what is this corner, and you contract everything into this one tensor, and then you do the same thing for this row, for this column, for this other, and then you build in this way this environment around your.
I see.
Right.
I see.
But Tony, I think it could be kind of mean field, but it shouldn't, because mean field is product of the states, and what you want to control is entanglement, right? So it's average, because this is the main idea of White and DiMarghi and all these things. You have to control the entanglement thing. And mean field is like product of the states. Probably it's not what you mean, right? But this mean field is forbidden in this field.
Phase transition too. It gives the phase transition.
No, indeed. No, but the point is that you want to keep track of the entanglement. So this environment is really to do the right truncation. You see, this is different from totally.
It's a kind of quantum mechanical mean field.
Of course, yes.
Yeah, something like that. Well, mean field normally is not the quantum mechanical in the sense of the classical.
Yeah.
Okay.
Yes. Okay. Very nice. It's kind of tricky, this thing, right? To do all this contraction, right? But there is indeed a fixed point. The fixed point is the consistency that Tony is talking about, right? This is the fixed point of the kind of RG.
Yes.
Yeah. Mm-hmm.
Yeah. So there's a certain criteria that you can use in order to see whether this environment is converged or not, and there are different things that you can look at in order to make sure that you have a converged environment. But these are all techniques that are very well known for nothing new. These are all, people have been using this type of techniques for studying 2D condensed matter systems for years. Well, maybe not for a long time, but there are some experts that have been using iPEPS and have developed all these ideas.
Other questions? Okay, so if not, thanks very much, Danny. It's hard to upload, but you can receive our virtual applause.
Thank you.
Thanks a lot for the seminar. Then I will stop the recording right now.